Auzubillahiminashaitanirajim. Bismillahirrahmanirrahim. Dear students, Assalamu alaikum. I am Dr. Azhar Ali, Assistant Professor, Electrical Engineering Department, Sarhad University, Peshawar, and you welcome back to this study. Dear students, today we are going to start a new unit for the course Bio Statistics 1, which is Introduction to Probability. So, for the week 10th, in this first video lecture, today we are going to learn about Introduction to Probability. So, first of all, I would like to tell you about the definition of probability. Probability actually is a quantitative measure of uncertainty, how likely something is to happen. The foundation of probability was laid down by two French mathematicians of the 17th century, Blaise Pascal and Pierre de Fermat. Now we are going to learn about an experiment. An experiment is a procedure carried out to support, refute, or validate a hypothesis. An experiment is a plain activity or process whose result yield a set of data. Experiment is a scientific procedure undertaken to make a discovery, test a hypothesis, or demonstrate a known fact. An example of an experiment is when scientists give rats a new medicine and see how they react to learn about the medicine. Similarly, an example of an experiment is when you try a new coffee shop but you are not sure how the coffee will taste. Now, types of experiment. Random experiment. An experiment which produces different results when it is repeated a number of times under similar condition is called a random experiment. A random experiment has three properties. Number one, the experiment can be repeated practically or theoretically any number of times. Number two, the experiment has always two or more possible outcomes. Number three, the outcomes of each repetition is unpredictable. Unpredictable. For example, rolling a die, throwing a coin. This is called a random experiment. These are the example of random experiment: rolling a die, throwing a coin. So in this case, we repeat the experiment: rolling a die, throwing a coin. Now, sample space. The set of all possible outcomes of a random experiment is called sample space. It is denoted by capital S. For example, tossing a coin. The experiment of tossing a coin results in is either of the two outcomes. One is head, denoted by H, and other is tail, denoted by T. The sample space for this experiment can be expressed as S is equal to, this is the sample space, because the set of all possible outcome of a random experiment is called a sample space. So in this experiment, because the experiment is tossing a coin, so when you toss a coin, we have these two outcomes. One is head and tail. So we will get either a head or tail. So the sample space contains these two outcomes, head and tail. Now another example of an experiment and a sample space. Tossing two coins. In case of tossing two coins at a time, with results in four possible outcomes. So the sample space contain these outcomes HH, HT, TH and double T. So when we toss two coin at a time, we obtain these results. We will obtain either in for both kinds, maybe we will obtain head and head. Similarly, maybe we obtain head for one kind and we obtain tail for other kind. Similarly, we obtain tail for the first coin and head for the second coin. And similarly, we may obtain at both kinds tail. So in this case, in this experiment, the sample space contain these outcomes. So sample space contain four possible outcomes. You see over here, double H, HT, TH and double T. Now sample points. Every element in the set of all outcomes of the random experiment is called the sample point. Like you see over here, this is a sample space. So these are the points of the sample space. Now event. Those subsets of the sample space to which probabilities are assigned by probability set function under consideration are called an event. For example, consider the random experiment of throwing a die and the sample space will be S is equal to 1, 2, 3, 4, 5 and 6. So if we have an experiment of throwing a die, then the sample space contain maybe these results. The sample space contain these results 1, 2, 3, 4, 5 and 6. Now a sample set, a subset of this sample space, suppose we have a set defined in even E is getting odd numbers, then E is equal to 1, 3 and 5. One can define an even E is getting odd number. So suppose we choose the odd number from this sample space, then the subset of this sample space E is equal to 1, 3 and 5. So this set E is a subset of the sample space. So this subset E is called the event for the sample space. Note that the event E is a subset of the sample space S. Now types of events. One type is a simple event and other is called compound event. If an event has only one outcome, then the event called simple event. That is, only one sample point is called simple event. For example, the event of getting head in the experiment of tossing a coin. Then in this case, the event has only one outcome. So in this case, the event is called simple event. Now if an event has more than one sample points, then it is called compound event. For example, the event of getting odd or even when ruling a die. So suppose when we ruling a die, then the sample space contain these points 1, 2, 3, 4, 5 and 6. Now if we select an event of getting odd or even, then suppose we are going to select an event from this sample space which contain the odd number, then the event contain these three outcomes, these 3 points. So in this case, this event has more than one point, so this event is called compound event. Now mutually exclusive event. Two events are said to be mutually exclusive if they cannot be happen at the same time. For example, if we toss a coin, either heads or tails might run up, but not heads and tails at the same time. For example, this is a sample space. S is equal to is contain the outcome head and tail. So when we toss a coin, we may obtain the sample space containing these outcome head and tail. Now suppose the A is the event of this sample space, and this A contain only one outcome, which is head, and now B is another event for the sample space which contain only the one outcome T. Now in this case, since these two event has no common element, A intersection B is empty set. So in this case, A and B are mutually exclusive event. So two events are said to be mutually exclusive if they cannot be happen at the same time. It's mean that two events which do not contain any common outcome is called a mutually exclusive event. Now another example, another type of event which is called exhaustive event. Events of a random experiment are said to be exhaustive if at least one of them necessarily occurs. For example, ruling a die. So when we rule a die, the sample space contain these outcome 1, 2, 3, 4, 5 and 6. Now for example, we have an event A, and this event A is a set of getting even numbers. Then this event A contain the outcome 2, 4 and 6 from the sample space. Now B is another event which contain getting odd numbers. So the event B contain the outcome from the sample space 1, 3 and 5. And C is another event of the sample space getting prime numbers. Then C contain outcome from the sample space 2, 3 and 5. 2, 3 and 5 are prime numbers. The event A and B are exhaustive events because when a die is ruled, at least one of the event A or B occurs. A and A union B is equal to 1, 2, 3, 4, 5 and 6. And this union is actually equal to the sample space. So in this case, A and B are exhaustive event. Similarly, the events B and C are not exhaustive. A is the union of these two sets contain the outcome 1, 2, 3 and 5, which does not equal to the sample space. So dear student, in simple wording, I want to tell you that two events will be exhaustive event if the union of their two events is equal to the sample space, and if the union of the two events does not equal to the sample space, then the two events will not be exhaustive events. Now equally likely outcomes. If all the outcomes of a sample space have the same chance of occurrence, then it is known as equally likely outcomes. It is not necessary that the outcomes are equally likely, but during an experiment we shall assume that the outcomes are equally likely outcomes in many cases. Now you see over here some experiment playing a card. In a deck there are 52 ordinary playing cards, and this all 52 cards are of the same size, and therefore it is assumed as equally likely outcome of each card, that is 1 over 52. Now another example of equally likely outcomes for this experiment, tossing a coin. During tossing a single coin, there are two possible outcomes. One is head and other is tail. It is always assumed that both are equally likely and each has a chance of occurrence, which is 1 over 2. If not, then the criteria should be mentioned. In case of tossing more than one coin, it is assumed that on all the coins, head and tail are equally likely. Now, in this experiment, throwing a dice. When we throw a dice, there are 6 possible outcomes when rolling a single dice. In this case, all the 6 outcomes are assumed to be equally likely outcome. Each has of occurrence 1 over 6. Now, not equally likely outcomes. When a sample space consists of outcomes that do not have an equal chance of occurrence, then the result outcomes are said to be not equally likely outcomes. A matchbox has 6 faces, but all the faces are not equally likely. Therefore, the occurrence of each face varies. Each face has different occurring value. Similarly, a bag is full of balls having different colors and size. Now, pick up a ball randomly from the bag. The occurrence of all the balls will not be the same. The occurrence of each ball will vary. So in this case, in these experiment, you see over here, the events are not equally likely outcomes. Now, basic definition of probability. One is called the classical definition. There are different approaches in defining probability. The oldest and simplest one is classical definition or mathematical definition. Now, definition. If a random experiment results in n exhaustive, mutually exclusive, and equally likely cases, m of them are favorable, where m less than or equal to n, to the occurrence of an event A, then the probability of event A denoted by P of A, this is actually probability of event A, is defined as probability of event A is equal to m by n. M by n. So, dear student, note that probability of event A is equal to m by n, where m is the number of outcome in the event A and n represent the number of outcome in the sample space. So, after a random experiment, we obtain the results. So, the results is called outcomes, and the set of all outcomes of an experiment will be the sample space. So for that sample space, we have a choice. So the set of our choice contain the number of outcomes, which is represented by m. Now this m is actually the number of outcomes of our choice set, and n is actually the number of outcome in the sample space. Then the probability of our event will be equal to the number of outcome in the event divided by the number of outcome in the sample space. So this is actually the definition of probability, and this is the classical definition of probability. Now, limitation of classical definition of probability. Classical definition of probability is very easy to understand, but the definition may not be applicable in all situations. Following are some of the limitations of classical definition of probability. If the events cannot be considered as equally likely, classical definition fails. If the events cannot be considered as equally likely, then the classical definition will be fail. And when the total number of possible outcomes n become infinite, this definition cannot be applied. So these are the limitation of classical definition. Because in the classical definition you see over here, a random experiment result has n exhaustio, mutually exclusive and equally likely cases. And this m is actually the number of outcomes in this event A, and the event A is actually is our choice. So the probability of the event A will be equal to the number of outcomes in the event A divided by number of outcome in the sample space. So if the total number of possible outcome in the sample space infinite, then this definition will be fail. The definition cannot be applied. And if the event cannot consider as equally likely, then the classical definition will be fail. So, dear students, note that a probability is a numerical measure of likelihood or chance that a particular event will occur. So, this is actually the definition of probability. Now, dear students, note that the no probability is negative. Probability of any event will never be negative. That is, the probability of an event will be greater than or equal to 0, and no probability is greater than 1. So probability of any event A will be will be less than or equal to 1. So no probability is greater than 1 mean that probability of an event will be less than or equal to 1. Now, frequency definition. Let the trials be repeated over a large number of times under essentially homogeneous condition. The limit of the ratio of the number of times of an event A happens, say m, to the total number of trials, say n, as the number of trials tends to infinity, is called the probability of the event A, which is denoted by probability of event A is equal to limit tends to infinity m by n. Now, axiomatic definition. The axiomatic approach to probability, which closely relates the theory of probability with the modern metric theory of functions and also set theory, was proposed by A.N. Galmogro. The axiomatic definition of probability includes both the classical and the statistical definition as particular cases and overcomes the deficiencies of each of them. On this basis, it is possible to construct a logically perfect structure of the modern theory of probability, and at the same time to satisfy the enhanced requirements of modern natural sciences. The axiomatic development of mathematical theory of probability relies entirely upon the logic of deduction. Now, axiom on probability. Let S be the sample space of a random experiment. The probability P is a real valued function whose domain is the power set of S, that is probability of S, and range is interval. Range is the interval, close interval 0 and 1. That is P. P is a function. So P is a real valued function, and this P, the real valued function, is a probability of S goes to. So the P real valued function, probability of S goes to this interval, close interval 0 and 1, and satisfying the following axiom. Number 1, for any event A, the probability of event A will be greater than or equal to 0 and will be less than or equal to 1. And probability of the sample space will be equal to 1. Number 3, if A and B are mutually exclusive events, then probability of A union B can be written as probability of A plus probability of B. So, dear student, note that I have already told you that probability of for any event will never be negative. So, the probability of an event will be greater than or equal to 0, and probability of an event will be less than or equal to 1. So it's mean that probability of the sample space will be equal to 1, because when we find the probability of the sample space, then the number of sample space divided by the number of sample space. So in this case we obtain the result 1. Now the conclusion of this lecture, dear students, note that in the conclusion of this lecture, actually the probability is a numerical measure of the likelihood or chance that a particular event will occur. This is actually the statistical definition of probability. And simply we can find the probability of an event. Note that how we can find the probability of an event. In this definition you see over here, suppose after an experiment we obtain some outcomes, and the outcomes uh, contain the outcome will be a sample space. So when we write all the possible outcomes of an experiment, we obtain a sample space. In that sample space we have a choice. So the numerical measure the numerical measure of our chance is actually called the probability that a particular event will occur. So the event is actually is a subset of the sample space. So the event contain actually our choice. So the numerical measure of the chance of our choice is called the probability of our choice. So I want to tell you again that the numerical measure of the chance of our choice in an experiment is actually called the probability of our choice. And how we can find statistically the probability of our choice? So actually our choice will be from the outcome of an experiment. So first of all we create an experiment, and after experiment we obtain all the possible outcomes, we obtain all the possible results of the experiment, and we put all the possible outcomes in a set, and the set is actually called the sample space. So in that sample space we have some choice. So the numerical measure of the chance of our choice is called the probability. And how we can find mathematically, statistically the probability of our choice? So when from the sample space we select our choice. So our choice will be in an event. So the event contain the number of outcomes of our choice. So we divide the number of possible outcome of our choice event divided by the number of outcomes of the sample space. So that will be the probability of the event which contain our choice outcomes. So note that after an experiment we obtain a sample space, and the sample space contain all the possible outcomes of the experiment, and from that sample space we have a choice. So we made a set, and the set contain all the outcomes of our choice, and the set actually called the event, because the event A, suppose the event A contain the outcome of our choice. So this event A will be the subset of the sample space, and the sample space contain all the possible outcomes of the experiment. So we divide the number of outcomes of event A, and event A is the our choice set, and this set is actually contain the outcomes of our choice. So the number of outcomes in the event A divided by the number of outcome in the sample space is called the probability of the event A. Now this is the end of this segment. Thank you. Allah Hafiz.